All right, well, welcome back. So in this section, we're actually going to be really quickly chatting about one of these really nice connections between the world of induction and recursively defined sequences. And we've actually alluded to this a few times already, this idea that when I start to build up some of these summation formulas, it very naturally is going to lead into this world of recursion. The idea is that I'm going to be using some previous information to actually help me guide myself into the next step. So to start this process off, we're actually going to be revisiting the very first summation problem that we looked at. The idea is that I want to add up all of the numbers from 1 up to some random stopping place, the so-called sum of the first n integers. So what you can see right here is honestly a copy and paste of that exact same summation formula that we saw in the very beginning of this section. The idea is that I can take 1 plus 2 plus 3 all the way up to a value of n. Well, what I could do is I could add up all of those, billion or trillion or zillion numbers or whatever number of terms I'm going to have, or I could actually use this really nice explicit formula that ends up kicking out as I run through this full induction process. So what we saw as we worked through this thing is that we can test this thing at a variety of different levels. The idea is that at level 1, the left-hand side is going to be a 1, and the right-hand side also turns into a 1. That ended up being my nice little basis step. That's what everything started with. The idea is that that was the process that got me onto the ladder. What I can do is that I can go one notch farther. I can go up to the second rung, and you can see that that left-hand side is then going to become a 1 plus a 2, which simply adds up to a 3. And if you plug a 2 into the right-hand side, it again is going to simplify down to a 3. Going up to level 3, I have a 1 plus a 2 plus a 3, which is going to add up to a 6. And if you plug a 3 into the right-hand side, it again is going to kick up a 6 as well. And as we started making this kind of larger and larger left-hand side, you very quickly realize that there's going to be this process that I'm going to be using the previous step to help me see the next bit. The idea is that if I wanted to look at what is 1 plus 2 plus 3 plus 4, well, if I know that the first three things are going to be a 6, I can make my work a lot lighter if I just simply replace those first three terms with the number 6, and then that's going to kick out an answer of 10. And that's exactly what's going to be happening as I slowly morph myself into this world of recursively defined sequences. The idea is that I'm just simply going to be recording these little numbers of 1 and 3 and 6 and 10. They're actually going to be entries in this large sequence of things. The idea is that my sequence is going to have a term that's going to be a 1, a 3, a 6, a 10. If I wanted to find the fifth term in this thing, what's going to happen is it's going to be a 1 plus 2 plus 3 plus 4 plus 5. But I know what 1 plus 4, or 1 up through 4 is going to be. That's going to be a 10 from the previous stage, and then I add 5 more. So the idea is that that's going to kick out a 15. So that's what we're going to be working on now, is going to be this idea of just simply recording those little individual terms as we go, forming a nice little sequence, and then actually proving that the sequence is going to be an explicit answer using this process of induction. So there's a lot of similarities that are going to be coming into play based on how we showed this thing initially and where we're going to be going in this world of sequences. So try to keep track of what world you're actually living in. Sometimes students, when they start to see these big summation formulas, lose some of that summation structure, and that's exactly what's going to be happening here, is that I'm not going to have this big sum of 15 or a billion terms. I'm simply just going to be recording that very last term, what that sum is actually going to be. Okay, so here's the full song and dance of what we're actually going to be looking at, so a little bit more eloquently written out. The idea is that these recursive definitions are going to bear some strong resemblance to this world of proofs by induction. The idea is that just like induction, you're going to be starting off with some very nice basis case. I may have multiple bases, I might just have one single starting place, but once I have that, I'm going to have some rule or expression that's going to show me how to actually climb this ladder. So what I have down below is going to be this world of a recursively defined sequence. So the idea is that the very first term, so I'm going to call it a sub 0, so there's a little bit of awkwardness that comes into play here, is that my sequence is going to start at a 0, but for those of you in the computer science world, this idea of starting at 0 is nothing new. You see that all over the place. So it works really nicely when I have my sequences starting at 0, and then I'm going to have an A1, and then an A2, and then so on and so forth. What my sequence is going to do is that once I have that initial term identified, what I'm going to do is I'm going to give you some rule that's going to tell you how to get the next entry. So in this case, what's going to happen is that my AN, which is going to be my new term, is going to be identified by taking the previous term, which is why there's that little -1 in the subscript, and then I'm going to be adding on that little index. So what I would do in this case is if I wanted to study what is A1, well, A1 is going to be the previous term, A0, plus the index. So in this case, my index was a 1. So I have a0, which is a 0, and now I'm going to have a1, which is then going to be a 0, because that's what a0 is, plus a value of 1, which is a 1. And if I continue this process, I can study a2, which is going to be an a1, the previous term, plus the index, which in this case is a 2, which in this situation is going to become a 1 plus a 2, which adds up to a 3. And if I look at a3, it's going to be the previous one, a2, plus the index, which is a 3. The a2 term we know is a 3, and a 3 plus a 3 is going to kick out a 6. And if I go one step farther, the idea is that a4 is going to be an a3 plus a 4. You can see that this is going to become a 6 and a 4, which we know is going to be a 10. So hopefully these little numbers over here look very familiar. They're the ones that I saw occurring over here as well. And that's what I was referencing, this idea that I'm going to be constantly recording where is my sum going to be going to in this case. The idea is that the sum of the first 1 terms, so a single term is a 1, the sum of the first 2 is going to be a 3, the sum of the first 3 is a 6, the first 4 is a 10, the first 5 then is going to be a 15. And that's exactly what this thing is going to be referencing. The idea is that a sub 3 is going to be the sum of the first 3 numbers. So 1 plus 2 plus 3, which makes a 6. So what I want to do in this case is I want to take this recursively defined sequence and make a connection between it and an explicit kind of object that's going to give me what the next term is going to be. The idea is that this recursive process is great and dandy, except for what's annoying about it is that if I wanted to know what is a sub 5 million, I would have to run this process 5 million times to actually get to that stage. So what I want to do is I want to transition away from a recursively defined thing into an explicitly defined sequence in this case. So what I can see is that I'm going to have some guess as what my formula is going to be. And that's where there's a little bit of kind of trickery coming into play, is that actually coming up with this explicit solution takes a little bit of work. There's actually some very nice theory that can take some of these recursively defined things and tell you what's supposed to be coming into play here. And you'll see some of that as you move into the actual discrete math class. Right now, I just want to mention that I can show these things are going to be matching using induction, but there's a little bit more going on behind the scenes of why this particular shape is coming into play is actually going to connect to what's actually happening up here in the recursively defined process. So that's what I have to work with, is I have 2 different ways to identify these AN terms, and I want to show that these things actually match. And to show these things actually match is going to be making use of this world of mathematical induction. Anytime I have this process that should be true for all values of n, that's where that alarm of induction, induction, induction should be firing off like crazy. So what I want to do is I want to show that using this top formula can actually be identified by that little bottom formula. So my expression Pn is then going to be that my explicit formula is actually going to hold. So that's the game that I'm playing with here, is that Pn says An is actually going to be this thing, even though An is actually defined like this. So what I want to do is I want to show that my basis is going to be met. The idea is that I should have P0 be true. Well, if I look up in my sequence world, I know that A0 is 0, and that's by definition. So that's a check. And on the other side, I can see that A0 is supposed to be 0 times 0 plus 1 all over 2, which is a 0. So that appears to check. So in that case, I do in fact have that my basis step is satisfied. So I'm at that stage that I'm sitting at the bottom of the ladder. Now what I want to do is I want to climb this ladder. So the idea is that I get to assume PK is true, and I want to show that PK plus 1 is true. So that's going to be my goal in this case. So what do I get to assume? Well, the idea that PK holds is going to be that this stage is going to hold at level K. That is, I'm going to take this answer that I have right here and replace those n's with a K. That is, I get to assume that AK actually looks like K times K plus 1 all over 2. And my goal, and if I change colors in this case to the blue that I like to work with, my goal, and actually change it to a blue. So my goal in this case, all right, maybe I can't actually change it to a blue. All right, I guess it's not changing right now. So theoretically, this should be a very nice blue font, but it doesn't appear to work so nicely. But what's going to happen is that my goal is going to be to have AK plus 1, which is going to be that formula up above, but with a K plus 1 substituted in for those Ks. So my goal is to actually show this is true. Or more simply, I can show that it's a k plus 1 multiplied by a k plus 2 all over 2. And if you'd like to multiply this whole thing out, that's fine as well. Is that if I distributed everything, I'm going to have a k squared, I'm going to have a 2k and a 1k, which is going to make a 3k, all of that with a 2 at the end, all over a 2. So if I can see this right-hand side occur for any of those things, I'm actually going to be able to be finished. The idea is that if I get to that stage, I know everything is great and I can stop at that part. So what do I get to assume now is I'm going to start with this recursive definition. And that's going to be the kicker on all of this, is that I start with that recursively defined thing. Because as of now, that's the only way I know how to identify these ANs. What I'm trying to show is that that formula works, but I have to start up here. Once I start up here, I can use that previous stage to simplify my work and hopefully get to this explicit answer, but right now I have to work with that recursive definition. So the idea is that I know that ak plus 1 is supposed to be the previous term, ak, plus the index. That's exactly how I built up all of those little terms that we started with. The idea is that if I wanted to study A4 is going to be A3, the previous thing, so 1 less than that index, and then plus that index 4. Likewise, A3 was an A2 plus a 3. So same thing here. I'm going to be looking at AK plus 1, which is going to be the previous one, so 1 less than this thing, which is a K plus 1 minus 1, which is a K, plus then that index of K plus 1. What I know here is I know what AK is, and that's going to be by my inductive hypothesis. So I can substitute in that crazy squiggly sun-shaped thing, and I can reference this thing now as AK plus a K plus 1 all over a 2, and then that's going to be added to another K plus 1. So my goal now is going to be to take this collection of terms and hopefully see one of these things up in the top actually kick itself out. What can happen is that I'm going to take this thing and I'm going to find a common denominator. That's what it's screaming to do on the right-hand side, so I'm actually going to go ahead and do that. So if I put everything over a 2, I'm good to go there. And now what I can do is I can actually combine those two fractions to get a k plus 1 multiplied by a k, and then plus a 2 times a k plus 1, all of that over a 2. So there's a couple things you can do here. One of the sneaky things to see is that I do have a k plus 1 in common on both of those terms. So I can actually factor out that k plus 1, and what I'm going to be left with is a k and then a plus 2. And then all of that's divided by a 2. If you don't like being so clever, another way you can go about this is you could take the k and you could distribute it. So I'd get a k squared plus a k, and distributing the 2 is going to be a 2k plus a 2, and then all of that's over a 2. And then if you were to combine these things, you could see that those middle terms actually turn into a 3k, and then that actually matches with this thing, or you could actually see that that thing is going to factor into that as well. So wherever you want to finish off that algebra, I like to try to be as clever as possible. Just the idea is that if I can avoid having to distribute something, I'm going to try to. So the idea is that if I can get to some stage where I'm trying to see things factored, that's going to be awesome. So if I can see that k plus 1, I'm going to factor that thing out and then try to clean things afterwards. So if I swing to the actual nice little written out proof of this thing, I actually have the color-coded side of things that I was hoping to see, but my pen was not cooperating. But the idea is that I'm going to go ahead and identify this Pn as being that phrase. An is going to be that explicit answer that I'm going to see for these terms. What I want to do is I want to show that that recursively defined process is going to match with this explicitly defined process. If those things are going to be true the entire way down, I know that these two sequences are going to be the exact same. So we know that they're going to be true at level 0 because they're both going to kick out a 0. So the next goal is going to be, okay, assume that it's true at level k, and then try to show that it's true at level k plus 1. So here's that part in red is what I get to assume, and I'm trying to work towards the part in blue. So what I have is I have my recursively defined process. So I have this recursive definition. So ak plus 1 is going to be an ak. That's supposed to be an a. There's a small typo in there. And then it's going to be plus that index k plus 1. So substituting what ak is, which is going to be that thing, and then still adding that index on afterwards, finding the common denominator of 2 in this case, combining those top parts, and then doing a little bit of factorization gives me what I'm hoping to see in that situation. So that's going to be this whole process. Hopefully it looks very similar to some of those early inductive arguments that we worked with. It's actually a little bit easier, I think, because it's a little bit less algebra because you don't have this massive sum going around. All we're simply doing is we're going to be recording what are the values of this big summation thing. The idea is that I'm simply just keeping track of 1, 3, 6, 10, and 15. I'm not having to rewrite that thing over and over and over and over again. So it's a super slick world to make this transition away from some of these summation formulas into the world of sequences, because sequences are going to be something that we're going to be working with a whole bunch. The idea is that anytime I want to think about a list of objects, those are simply just going to be entries in some massive sequence. If I want to have this sequence having an infinite number of terms, what I can do is I can start to represent those things explicitly, or I can use a recursive definition, and this is going to be showing that those two worlds sometimes actually match up very nicely. I would prefer to have an explicit one, but if I do have a recursive thing, I can hopefully try to make a nice explicit answer out of it.